Lesson 5.3, connecting the derivative and second derivative with the graph of the function. There's a lot here. I'm going to jump right in. It says in the diagram above, and I made this once upon a time with some weird software, show the derivative in each interval and at each critical point. Reminder, critical point is where f prime equals 0 or what we call a point of interest. F prime is undefined, might be a vertical asymptote, might be a corner, something like that. Oh, I just realized you didn't see that. F prime equals 0 or point of interest. So critical point is where, what do they call it? A stationary point is where f prime equals 0. Critical point is what I call a point of interest. So anyway, up here, let's see what's going on. So here the derivative is greater than 0. Here it peaks out. The derivative is equal to 0. Here the derivative is greater than 0. Here the derivative equals 0. Here the derivative is less than 0. Here the derivative equals 0. Here the derivative is greater than 0. Here the derivative is undefined. Here the derivative is less than 0. Here the derivative is equal to 0, and here the derivative is less than 0. Now, you might be like, well, duh, we've been doing this for a while. We've got slopes and peaks and valleys, but here's a definite peak, but here is not a peak. It goes up and then it keeps going. It's going to be a point of inflection. Going to be another point of inflection here. This one's a little more obvious. Your point of inflections are where you go from concave up, curvy up. I use my fingers, kind of a C shape up, and then to concave C shape down. So this would be a point of inflection here. It's concave up, and now it's concave down. I like to think of it as the derivative is getting more and more and more positive. And then the point of inflection is where the derivative starts to come back. It might go all the way to here, and then it starts to come back. Basically, you set the second derivative equal to 0, and off you go. So here's tons and tons and tons of definitions. At a critical point, if the derivative changes sign from positive to negative, it's a local max. So that's this here. It was positive, and now it's negative. It's a max. We also have a min, but that's coming up in the very near future. So here we go. F prime over here, positive, greater than 0. F prime over here. So this would be a max. Local, relative, we don't know. We don't get into that. But notice it also works for a cusp, where the derivative is greater than 0 and the derivative is less than 0. So we'd be able to call this a max, even though the derivative is not defined there. So we've got to be very intelligent with how we do this. Can't just slap things on the page and say, good enough. Got to look at graphs and got to analyze things and be wise. So now the flip side, and again, I'll do it as a corner this time. Derivative is less than 0. Derivative is greater than 0. Derivative is less than 0. Derivative is greater than 0. So we have a min. And then if it doesn't change sign, so here the derivative is greater than 0. Here the derivative is still greater than 0. So that's not a max or min, but it is point of inflection. Over here we have POI. F prime is less than 0. F prime is less than 0. Now, we also can check out the endpoints. It's kind of ludicrous, but obviously it works. So if the derivative is going down, that's a max. If it's going up, that's a min. That was from a left endpoint, and then we do it again from a right endpoint, which is kind of silly, but what are you going to do? So that's a min because f prime is less than 0. That's a max. And what they're doing here is really desperately trying to digitize all this so you don't have to think that hard. F prime is greater than 0. But I don't buy that. You got to think, you got to use your brain. You got to make sure you're being intelligent about these things, right? So we talk about the first derivative test and the like. I don't get too hung up on it. It's very rare that I've seen in questions say use the second derivative. It's usually like I just said, let's be intelligent about this rather than just blindly follow us, oh, we're using the test. I don't know what that means. We'll just run with it. We're usually a lot more wise than that. All right, so set that equal to 0. That's the first derivative test. So we go and we throw it on our number line here. There's no corners, no cuts. I'm not worried about anything here. I don't have a weird graph, so I'm not going to look at the graph too much. I mean, it's next to the third, so it's going to be doing something like this. So I plug in 0, which is my favorite, into the derivative. This is kind of important. I get a negative. I plug in 3 into the derivative. Now 3 is 27. I get a positive. I plug in -3, and I get the exact same thing because it's squared. So yeah, that's where I got positive, negative, and it looks like there's a max and a min here. And you can look at it. Here's a max because that's a peak. Here's a min, that's a valley. So I would normally say max occurs at x equals -2, but I'm just being lazy right now. Max and a min. And the local extreme values, that's not very good. And by the way, it's a relative max. Looking at the graph, relative min. We should say at x equals -2, there's a relative max of, plug in -2 here and see what we get. Again, I'm being a little lazy on this one. Keeping the show moving. Over here, derivative, g prime of x equals, leave it. Derivative 2x, that was the derivative, leave it. So e to the x times x squared minus 3 plus 2x equals 0. E to the x never equals 0, so I can pretty much ignore it. X squared plus 2x minus 3 equals 0. So to find out what it equals 0, I go x plus 3, x minus 1. Looks good. And I get x equals -3 and 1. Number line it. Notice I don't try and make my number line perfect. Just keep it moving. Plug in 0 to the derivative. E to the 0 is 1. So this is always positive. I can kind of ignore it. I'm going to plug it in here. 0 minus 3, so it's negative. Plug in 2. 4 minus 3 is 1, positive. Now -2 is going to change everything, so I'm going to plug it in here. 4 plus -4 minus 3, so I got negative. It's because I plugged in -2 like a knucklehead. How about -10? I get 100 minus 20, that's positive. So here we have a, I'm going to just say max. And here we have a min. I would have to graph this to say, is that a definite max? Is that a definite min? What is going on here? Well, let's talk for a second. Let's think for a second. E to the x is going to take off. So that's going to dominate. So it's going to get really tall. So this is going to be a relative max. Now e to the negative infinity gets closer and closer to 0. So this sucker is only going down as far as 0. So I would plug in 1, get -2 times e, which is like less than 3. So it's like -5 point something. So the value down goes to -5 here. And let's plug in negative a gazillion. It's basically 0. This is like an absolute min, unless I'm mistaken. I did not want to take forever. Ow. But I am going to have to graph that. Just talking to the wall, you probably couldn't hear me. I am going to have to graph that, see what's going on, see if I get it right. I cannot overstate how careful you should be in setting up your graph and double check it before you run off and graph it, because I've done this so often where I go, wait, my graph tells me something else, and then I feel like a knucklehead. So like I said, it basically goes to 0 out there. I don't see the relative max at -3. So I'm gonna have to zoom in, but I definitely got the absolute min right, and it's definitely a relative max if I got it right. So let's see if I can get in over here at 1, 2, 3. We should see just barely a hill there before it goes down. That's pathetic. Zoom in again. There it goes up, and there it goes down. There is a max there, just barely. So zoom 6. There's a max at -3. There is an absolute min at 1. Interesting. Let's know what the heck we're talking about. Maybe. So concavity means curvy up. This is the two choices. All right. Concave up. And I do the fingers up or down. I really hope that came across on the video. I wouldn't count on it. And we get the second derivative to find where it's concave up. All right. So they talk about y prime increasing, meaning the second derivative is positive, concave down, y prime decreasing. So it's really easy. So we'll just take the second derivative. And if we get a positive, we're good. And we get a negative, positive concave up, negative concave down. That's it. It's that quick and that simple. Sometimes it's a real pain to take the second derivative. I can guarantee that. It's never what I would call easy. X squared, we know, looks something like this. So it's going to always be concave up. So we're going to take the second derivative and find out that we have dy dx, we have a positive value of 2x, d squared y dx squared equals 2 positive. And we're going to say always concave up. I'm not even getting into this 3 to 10 thing in terms of throwing in numbers. But I mean, that's how I would write it. So now 3 plus sine of x up here is going to do this. So it's going to bounce around. We're from 0 to 2 pi. So we're going to get concave down, 0 to pi, and concave up from pi to 2 pi. Let's see how I do. dy dx equals cosine of x squared y dx squared. By the way, it's a lot easier to go y prime, y double prime, but I'm purposely doing that. Negative sine of x. So we set that equal to 0. All right. Where does negative sine of x? It should be in red. Very, very ashamed that I made it in blue. OCD's kicking in. Negative sine of x equals 0. X equals sine of x equals 0 at 0, pi, and 2 pi. And I shouldn't be using those because it's not in the interval, but I know I should cross those out. I'm just trying to figure out what's going on. So let's check it out. Let's go. We can't use, so it's right at the end, 0, pi, and 2 pi, but we can figure out what's going on here. So plug in pi over 2. Sine of pi over 2 is 1, -1. So it's, I blew it. Disappointing. It's concave down. There we go. Negative. And plug in 3 pi over 2. Well, Sine of 3 pi over 2 is -1. Negative, negative is +1. So it's concave up. So I would say 0 to pi, concave down, pi to 2 pi, concave up. And notice I didn't use the endpoints. So point inflection is where the two change. That's where we set it equal to 0. I couldn't use 0 or pi. So at pi, we have the point of inflection. Changes from concave down to concave up. All right. Now I'll go and be lazy and use y double prime. Second derivative equals 0. And let's read this. Point inflection is point on a graph where the function has a tangent. That could be vertical or horizontal. Just be aware of the tangent idea. But this definition, by the way, memorize it. I've had times where I get lost in a problem. And it happens a lot in calculus, but in this particular case, is it a point of inflection? Okay. Is there a tangent line there? Second derivative equals 0. Cool, cool. And does concavity change? Oh, yes or no. And now I know what the answer is. So yeah, remember that. That causes problems. This is a interesting example. Y equals e to the negative x squared. Let's be lazy. In terms of writing dy dx, y prime equals e to the negative x squared times negative 2x equals negative 2x e to the negative x squared. Y double prime equals, leave it. That's the same derivative, negative 2x e to the negative x squared plus, leave it, negative 2 e to the negative x squared equals 4x squared. I'm going to factor right away, e to the negative x squared. E to the negative x squared. No matter what I put, it's going to be e to the negative, right? So I know an e to the negative x graphs down, but it's always going to be negative no matter what I put in there. So when I put in a really, really huge negative number, so I think it's going to look like this. Let's see if I'm correct about that. And I am getting a little bit away from what we're trying to do here, but I always test my knowledge of graphs whenever I can, because it really is important to know what you're talking about. So I expect it to go like that. Wow. I actually know what I'm talking about. Scary. Although I would have thought this would have been a cusp here. That's a nice smooth line. Maybe it is. Zoom in. Don't think so. Looks pretty smooth to me. Yeah, right. Anyway, so this is always positive. So when I set this equal to 0, I only care about this part again. 4x squared minus 2 equals 0. X squared equals 2 over 4. X equals plus or minus square root of 1/2. X equals plus or minus root 2 over 2. Negative root 2 over 2, positive root 2 over 2. Okay, plug in 0 to the derivative. Always positive, who cares? Either the 0 is 1. Negative 2, so negative. I'm not going to screw it up again, I hope. Concave down. Plug in 100. It's a big honking positive number. Concave up. Same thing for the negative 1, because squared away, concave up. So we have POI, points of inflection, at negative root 2. I'm going to do it right this time, comma something, and positive root 2, comma something. Let's see if I plug this back into the original. That's the square root of 1/2, so square root of 1/2, e to the negative 1/2, also known as 1 over root e, is the same thing, 1 over root e. So let's guess what the graph looks like. And I'm not going to draw it in because I'll be super wrong and feel stupid. But it's concave down. What does it hit at 0? It's 1. So here we go. We go concave down. It's going to bump up. As we go out to infinity, we saw what happened. So it's going to do this. It's going to go on the line and go over here. Wait a minute. I already graphed this. No, I didn't. Yes, I did. Moron. So there it is. Check it out. Point of inflection at root 2 over 2, which is, I don't know what it is. 0.704? Yeah, 0.707. Oh, come back here. Graph. So at about here, there's point of inflection, concave down, and then a concave up. That's really funny that I did that. Kind of didn't realize what I was doing because we got so lost in the calculus. Oh, what a terrible drawing. Onwards, because again, this is a long stinking video. Look at the graph of the derivative of a function. Oh no, this is f prime of x, and I would like underline that like 19 times. Oops. All right, I gotta read this. Where's the graph increasing? Where's the concave up? What are the x-coordinates with local stream inflection? So this is brutal. Really, really, really hard. Well, let's do first derivative test. Where are my zeros? I told you I always go with zeros. So I'll even write this in. First derivative test. I'll put a question mark there. And then I realized I was stupid. Geez, I'm not putting anything on the drawing. I'm going to put a question mark here. And so instead of put an exclamation point, there's really no reason there's an exclamation point there. We want to know where the derivative equals 0. So we have -2, 1, and 4. The value is positive, positive, negative. So from 1 to 4, we get negative. 4 and above, positive. From here to here, we get positive. Here to here, we get positive. So I'm guessing point of inflection here, but we'll check with the second derivative test. Max, there's a max at 1. And max occurs here. The graph is increasing from here all the way to here because those are positive values, meaning it's a positive derivative. It's decreasing from here to here and increasing again from there to there. So increasing, 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 decreasing, decreasing, increasing. This is probably a relative max because it keeps going up forever. Relative max at x equals 1. And no, we definitely aren't getting a value out of this because it's just derivative. And then we have a increasing, decreasing. This is going to be an absolute min. You will never have to say that. You won't have to say relative or whatever. Now, second derivative test. I'm going to put an exclamation point on here because I don't want it to feel bad, like it's not as important as the first derivative test. We're looking for where we have peaks and valleys here. So there's one at -2, there's one at 0, there's one at 3. All right, make sure we're clear about that. The slope of this graph, now we're not talking about the values, negative, positive, negative, positive. Negative, positive, negative, positive. It's crazy, huh? You got to keep it all that straight in your head. Down, up, down, up. POI at x equals -2, 0, 3. That's a lot of work. Man, you really got to know what you're talking about there. That's tricky. All right, more. Told you it's a long set of notes. Down to 3 pages to go. That's huge. It's crazy. Particle moving along the x-axis with position function, find the velocity acceleration, describe the motion of the particle. Going to keep this show on the road. V of t equals x prime of t equals 6t squared minus 28t plus 22 I'm going to cheat and say set this equal to 0, and there are zeros at t equals 1 and 11/3. If you did all the work, let's just check. 6 minus 20, yeah, definitely 1 works. I'm going to assume 11/3 works. So here we go. Let's find out what's going on now. 1 and 11/3. 11/3 is stupid. It should be 3.67, so I can do this easier. That's fine. Plug in 0, I get a positive. Plug in 2, that's a little trickier. 4 times 6, 28, 24, ouch. Plus 22. 46 minus 2 times 28, negative 56 is going to be negative. And then a gazillion in here makes that square dominate. So this is where it's moving right. This is where it's also moving right. This is where it's moving left. All right. Let's go find the acceleration. A of t equals 12t minus 28. Zero and t equals 7/3. Off we go again. 7/3 is negative and positive, concave down, concave up. So you would say that it is decelerating and accelerating. That's it. Decelerating, accelerating. Now, we are going to cover logistic growth another time, but I want to get you a taste of it. Okay. Population of Alaska is used by this logistic growth. Here's what logistic growth looks like. And it has a limiting factor here, a horizontal asymptote. So what's going on? Well, this really isn't usually population of a state because people have this infinite ability to maximize resources. Some people would argue we're starting to bump up on it soon, and I would not disagree with them. I would say, let's see what happens because we're just amazing. If we can find a way to generate clean energy forever, then we can recycle anything. It's kind of a neat process. But Alaska really only has so much that you can get to it. Only so many people want to move there. So its maximum population is believed to be right up here. Actually, I should go look that up, but let's just say that's accurate for now. That they're looking at just a little bit more than 846,003 total population. So that's what this means. And we start with a ton of people and we accelerate rapidly. We are concave up. F double prime, go with Y. Y double prime is greater than 0. We are increasing. But after we hit the POI, we get to Y double prime is less than 0. We're in decline here in terms of the population is becoming less and less and less. Now, you could argue it's going to hit a max kind of stabilize there. Most places it actually heads down, like it is in Russia, Italy, Japan, things like that. The Chinese and I'm not sure about the Indians. The Chinese are in here somewhere where they have this massive population, but it's starting to peak out. And people don't want to have more than one kid after years of being told that. Here's the interesting thing. Everybody's told, this is time. I put an X up here, but it's really time. This is population. Hey, we got to figure out where the T happens. Well, actually, here is, it looks like my pen's dying. Half of the max population. And that's a question I see a lot on AP exams. Sorry, I just had to dig for a new pen. Where will the population, where will the point of inflection occur when the population's half? oh, well, we have to know when that is when we can put this in and try and solve it. It's a nightmare. We'll show you how this happens and what all these numbers mean. But the only one you need to remember is just the max population. All right. It's never going to get up. If you plugged in 2020 in here or 120 since 1900, you're going to get a number that's less than 846,000. And I would go through it, but we got to keep moving. So already done the second derivative test, already showed you this. Find the local extreme values. And they say, like, take the second derivative, it's less than 0, greater than 0, and off you go. You can figure out maximums that way. Sure, whatever. So f prime of x, and I actually do this with first derivative and second derivative, because I think that's a healthier way to do it. Get your zeros at x equals -2, 2. So we slap them onto this. Plug in 0, we get -12. Plug in a monster number, we get positive. Plug in a monster negative number, we get positive. So we got this going on. So we're going to have a relative max here and a relative min. All right. If we do the second derivative, we will find, and I'm not doing the math there because it's obvious, negative and positive. Think about it, plug in negative, positive. So you should be able to look at this and say, well, it's concave up. There'll be a relative max up here somewhere and a relative min over here somewhere. But I like to put them together. So I usually skip this, but I think I'll go over it. Here's the derivative. Identify where the extreme occur. 4x third minus 12x squared equals 0. I'm winging it here. 4x squared. X minus 3 equals 0. So we have a x equals 0 and 3. Got some weird stuff coming at us here, but that's okay. So we get paid to check out. You're lucky. Plug in 1. I'm going to use this right here. I think it's easier. This is always positive. So 1, negative, done. 4, positive, positive. -4. Ooh, I got to be careful. Positive, negative. I ran with that in the wrong way. So that is the derivative. Interesting. So second derivative. F double prime of x equals 12x squared minus 24x. Zeros at x equals 0, comma. Let's take out a 12x, left with x minus 2 and 2. Should be a point of inflection in here where we go concave up. And then here is going to be where we go, I don't know, let's go find out. 0, comma 2. Plug in 1, 12 minus 24, negative. Plug in 3, plug in a gazillion, that's going to dominate, positive. Plug in a negative gazillion, that's going to dominate, positive. So this is concave up, concave down, concave up. These are POIs at x equals 0, comma 2. So this graph is concave up. Let's jump to the next page. I'll go back and forth. Actually, let's see if I can do them both. That's almost enough space. We're almost there. Cool. Now, to complete the picture, we really just need a point on the function. So we're just going to guesstimate. We don't have it. But we know it's got a negative slope, right? All the way up to 0, it has a negative slope, and then has another one. And it's got a point of inflection. It's up here and then down here. It looks like it's going to do something like that. So the point I've picked is at 0, 0, which is ludicrous. But there it is, concave up. It's going to be concave down out here till 2. And then there's going to be a minute 3. So what in the heck? How do I draw that? Concave down. It looks like I would do something like this. And right here, it starts going up again. And the slope is positive from here on out. Let's see how I did. And slope is positive from 3 over and negative before that. Negative, negative, down, down. And then there's a horrible looking point of concavity here and here where down should have more curve. Something like that. Yeah, there we go. And this could be anywhere up or down. I just picked the point at 0, 0. Very cool. So remember, a function can be continuous they'll have points of non-differentiability because of cusps and corners and all that fun stuff. So here's a really, really beautiful example. Non-continuous graph of the derivative could give you a nice smooth graph of the function, right? So here's a function that's continuous. It's going to have cusps and corners, you know that. 1, 2, 3, 4. 1, 2, 3, 4. Don't know where it starts. Could be anywhere. So let's just keep it simple. Is the derivative, right? Positive slope. So it's got to be going up until negative 3. There's a point of inflection at negative 2. Right? How am I going to draw this? So that means it's positive slopes going up. Yeah, and then at negative 3, it starts coming down. Positive slope. So that's it. This is y equals f of x. Why we're calling it y, not just f prime of x. I have no idea. All right, but having a point of inflection is just constantly doing this. Now it's going to change here at negative 2 or 3, 2. On its way down, oh, now it's going to change its mind and want to start going up again. And it's going to have a min at 1. Really help if I labeled these. Purposely not labeling this axis because I don't know what's going on. I don't care. I don't have anywhere to work off of. Min right there. Okay. Slope is positive until it gets up to here. And then bang, we hit a cusp and it goes negative. It jumps. So ignore this little tail end here. And it is negative slope down to positive slope with a point of inflection at 1. No, a minimum at 1. No, there's no point of inflection. So a minimum at 1. So it's constantly doing this up until 2. At 2, it suddenly drops down and has a constant slope of negative 2. Boom, it's at a fairly steep angle here. I should put a point there. Plus out that, point there. Something like that. It's brutal, not easy. You're gonna have to do a lot of practice on this. But after you bang your head on it, it gets a little better, not a lot. Really should learn to lie more effectively to my students. Good luck and happy mathing.